Thanks for your patience waiting for us to work out the office hour schedule. They were posted over the weekend. TAs are going to begin holding their office hours today, and we'll continue on this schedule for the next, until the end of the semester. There will be one or two changes from time to time, and we'll announce them using an instructor's note on Piazza when that happens. My own office hours, I had to vary them in order to accommodate other TAs' schedules. So the way my office hours are going to work is this week I'm holding them Wednesday 10:15, Thursday 1:15, and then in the following weeks after that, it's going to be Tuesday, Thursday at 11 o'clock on Tuesday and 1:15 on Thursday. If you need to see me about anything and your schedule doesn't allow coming to either of my office hour time slots, you can always write to me and make an appointment to meet me out of band. Those are all the announcements for today. And now I want to talk about analyzing this algorithm, the proposal algorithm for the stable marriage problem, stable matching. So just to refresh your memory of where we were, we're designing an algorithm to assign job applicants to employers. Each side of the market specifies their preference ordering over the alternatives on the opposite side of the market. So the input consists of n ordered lists of employers, one for each applicant, and n ordered lists of applicants, one for each employer. And the objective is to output a perfect matching. That's a one-to-one assignment of applicants to employers, so that the unstable situation does not occur. And the unstable situation is represented by two applicants, A and B, two employers, X and Y, such that A thinks Y is better than X, and Y thinks A is better than B. Any matching that has a little configuration of two applicants and two employers matching that prototype is considered unstable because after the centralized market says I'm matching A with X and B with Y, there could be an aftermarket where A and Y decide they would like to deviate from their recommended assignments and match with each other. And so the mechanism itself is not self-enforcing. You would have to have some kind of external authority that says, if two parties break from the intended assignment like that, I'm going to punish them somehow. A stable matching, such as the one that this algorithm is going to output, is self-enforcing in the sense that there's no two parties that would mutually agree to deviate from the recommendation. Okay, so at the end of the lecture, I wrote down some pseudocode for an algorithm to solve this problem. We haven't gotten anywhere on analyzing it. And in fact, the last thing I did before dismissing you was to point out that there were several improperly specified or underspecified things in this algorithm. One thing that was underspecified was if there's more than one unmatched employer, which one do you choose at the beginning of any iteration of the while loop? It was intentional to leave that unspecified because in this and many other algorithms, it's permissible to write a general algorithm specification that the programmer can implement their own tie-breaking rule when you come to an ambiguous step like that, as long as the correctness of the algorithm is valid regardless of the tie-breaking rule that the programmer applies. But there's another more serious problem with the pseudocode, which is that the first line of the while loop says X proposes to the highest ranked applicant it has not yet proposed to. There's a corner case that's not covered in this specification, which is what if X has already proposed to every applicant, then the behavior on that line is not defined. And so I'm going to get around that by modifying the pseudocode and say, while there exists an unmatched employer X who has not yet proposed to every applicant. Now I think the behavior of every line of the code is defined. And by making this change, we also got another property that's going to be desirable, which is although the code contains a while loop, I'm no longer worried about the possibility that it could run infinitely long without terminating. And that's because there's an upper bound on the number of while loop iterations that can be deduced from thinking about the code for a minute. Does anybody see the upper bound on the number of iterations of the while loop? Yes?
Every single employer proposing to every single applicant?
That's right. So that would amount to n squared iterations. Okay, so okay. So we're getting pretty close to a runtime analysis of this algorithm, because the entire algorithm consists of a trivial initialization step, a loop where we just bounded the number of iterations. So to figure out the running time, the only thing that remains is to count or bound from above the number of operations that might have to be performed in any single iteration of the while loop. Okay, so fact 2 is that every iteration of the loop can be implemented to run in order 1 time. This requires choosing the right data structures in various places. And all of the data structures are elementary, but you might have to tinker for a while to figure out how to get every one of these operations to take constant time. Let's go through them. So X needs to be able to find the highest ranked applicant it has not yet proposed to. A natural way to accomplish that in constant time is the input already contains an ordered list of X's applicants ranked from highest to lowest. We can assume that that's represented as a linked list. So you could just have an iterator in each of those linked lists that's pointing to the most recent applicant that each employer proposed to. When you reach this line for employer X, you just move the iterator to the next item on the list. And finding the next item on a linked list is constant time. Y needs to be able to check if it's matched. Okay, so we'll have a Boolean array for all the employers and all the applicants containing a flag that's set to true if they're matched and false if they're unmatched. Y needs to be able to compare its current match with X. Okay, so for this you actually need to create, this is actually the list 1. So to do this in constant time, if the natural input representation for Y's preference ordering is a linked list, right? So when Y receives a proposal from X and Y is currently matched to Z, the naive implementation would be find both of them in the linked list, note the index where they occur, and compare those indices. Finding an element in a linked list takes potentially order n time, so we need to do better than that. So the trick here is that every applicant Y makes a reverse index during a pre-processing step that goes here. Okay, the reverse index is an array that inputs, the reverse index is an array where you input an employer number and you look up that index in the array and it tells you the rank of that employer on the applicant's list. Okay. For each applicant's list, it takes order n time to run through it and generate this reverse index. So it takes order n squared time to create this reverse index. And once you have it, in order for Y to compare its current match Z with its new proposer X, it just needs to look up those two entries in the array. The array values tell it the position of Z and X on its preference list, and it compares those two numbers. Okay. Finally, the last line, X and Y become matched to each other. Okay, so that's updating one Boolean flag in an array representing the matched pairs. And the previous partner of Y becomes unmatched. That's updating another flag in the array of flags that says who's matched and who's not. Okay, so that so if we do order n squared pre-processing steps, to build reverse indices, then every iteration of the loop can be implemented to run in order 1 time. And so the conclusion is that the running time of the entire algorithm is order n squared. N squared time for pre-processing and another n squared loop iterations, each taking constant time. Any questions about the runtime analysis? Okay, so now we come to the big question. Why does this output stable perfect matching? And there are two easy properties that are going to be key to resolving this question. And I'm going to call them property E and property A, standing for employer and applicant. So from the viewpoint of an employer, one single employer, what happens in this algorithm is for any employer at any stage of the algorithm, the set of applicants they have proposed to is an initial segment of their ranking of applicants. They go through applicants in order from most preferred to least preferred, making proposals to them in that order. So if you pause the algorithm at any moment, the set of proposals they've already made is some initial segment of that ordering. In general, invariants like this I deem to be so obvious that they don't require proof. However, since it's early in the semester and we have not been working with each other long enough to establish common knowledge about what deserves to be proved and what doesn't, I'm going to err on the side of caution, as you should when doing your homework, and actually write down a proof. While writing, to make it crystal clear, this step would be deemed unnecessary in a homework solution. So call the employer X. We're going to prove the property by induction on T, which denotes the number of while loop iterations. The induction hypothesis is that after T iterations, X has proposed to the first I of T applicants on its list for some value I of t. Okay, in the base case, t equals 0. X has proposed to no one. So the statement is true by setting I of t equal to 0. In the induction step, assume that it's true for t minus 1 iterations. Then there are two cases. Case 1 is that the employer chosen in iteration t is some z not equal to x. Then the set of proposals X has made is unchanged, and I of t will be equal to I of t minus 1. In case 2, the employer chosen in iteration t is x. Then x proposes to the highest ranked y that it didn't yet propose to. The position of this y on X's list is 1 plus I of t minus 1 by definition of I of t minus 1. Therefore, the induction hypothesis holds true after iteration t. By setting I of t equal to 1 plus I of t minus 1. End of proof. Any questions? I should get the whole property and its proof on the screen at the same time. Questions about that step? Yes?
Doesn't this assume that they're unmatched for the entirety of the loop?
They meaning X and the person it proposes to?
Right. If X isn't unmatched, then during a certain loop iteration, they don't propose anything. And then I of t shouldn't.
Right. If we look back at the code, the only way X could possibly be chosen at the start of the loop is if it is unmatched. Okay. So if X is matched, then we're always in case 1, which is that the employer chosen is some z not equal to X. Yeah. Good question. Okay. So that's what things look like from an employer's standpoint. It starts at the highest ranked applicant, and it just proposes to them one by one in order from the beginning of its list onward. The next property we're going to articulate describes what the situation looks like from the standpoint of an applicant. After the first loop iteration in which applicant Y receives a proposal, Y remains matched throughout the remainder of the algorithm's execution. And the sequence of partners, let's say employers, to whom Y is matched form an increasing sequence in Y's ranking of employers. Okay? From the standpoint of an applicant, they start out unmatched. They become matched the first time they get a proposal, and then their prospects just keep getting better and better. This property, again, has a proof by induction that I would write down if I were being pedantic enough to go through this step. Again, I'm going to deem this property to be obvious enough that if you were writing this analysis on your homework, you wouldn't have to include its proof. But let's go back and look at the code, and let me explain why I think the property is obvious. Okay. First, let's talk about once Y becomes matched, it never becomes unmatched. The explanation for that is the only time the partner of Y is changed is when we're in this step. Whoops, not that step. Be nice. Oh, you can't. What the heck is going on? Ah, much better. That's interesting. So when I circle something on my screen, it vanishes for you. Is that what you're telling me? Let's try this out. I'm going to make fact 1 disappear. Yeah. We're good? We're good. This line of the code is the only one where anyone becomes unmatched, and it's the previous partner of Y. You know, this is the only step where Y's matching changes at all. And what happens is Y breaks off an engagement with a previous partner and becomes matched to X. And furthermore, that step only takes place if Y prefers X to the previous partner. So that explains why the sequence of matches forms an increasing sequence in Y's ranking. Oops. Okay, so let's, we've got property E and property A now. We need to prove that we get a stable perfect matching at the end of the algorithm. So let's work on perfect matching first. Okay, this one is actually quite subtle. It's going to be a proof by contradiction. So suppose that employer X is unmatched at the end. Do you remember the termination condition of the while loop? Let's go back and review it. The while loop runs as long as there exists an unmatched employer who has not yet proposed to every applicant. Okay, so if we terminated and there's an unmatched employer, we may conclude what? They've proposed to every applicant. Okay. Okay. Remember property A. Once an applicant has received a proposal, they remain matched forever until the end of the algorithm. Okay. So if every applicant has received a proposal, then they are all matched. Okay, so at this point we have we have that X is unmatched. So we have strictly fewer than n matched employers. We have that every applicant is matched. So that means we have n matched applicants. So now the pigeonhole principle kicks in and says some employer is matched to 2 or more applicants. But this contradicts the logic of the algorithm, which maintains an invariant that every employer is matched to at most 1 applicant. Okay, in a super careful proof, you would use induction also to establish that invariant. Okay, that's the proof of perfect matching. Questions? Okay, second claim, the perfect matching. That the algorithm outputs is stable. This is again going to be a proof by contradiction. The previous claim, I described it as subtle because it's not obvious that it should be proved by contradiction. This one is almost begging you to prove it by contradiction because the definition of stable is the non-existence of a forbidden configuration of preferences. Okay? And usually the way you're going to prove non-existence of something is you start out by assuming it exists and obtain a contradiction. Question?
Previous proof account for the applicant being unmatched at the end.
That's right. First we need to know that every applicant has received a proposal. But we get that because of the termination condition. They've received a proposal at least from X and possibly from someone else. And then property A kicks in because every applicant has received a proposal. It guarantees that they all are matched. I have a feeling you would feel better about this if we went back and looked at the pseudocode and made sure that after you've gotten a proposal, you can't become unmatched. I'm willing to do that.
Well, I'm just wondering because it assumes that we terminated because they had already proposed every applicant?
Well, we terminated because every employer was either matched or had proposed to every applicant. But well, that's right. If every employer is matched at the end, then we've already got a perfect matching. So the only case we have to cover is that there's one that's unmatched. Yeah. Okay, so this proof is going to be by contradiction. And again, let me draw the forbidden configuration. So suppose that AX and BY are matched at the end. But A prefers Y to X. And Y prefers A to B. Oh, I did something bad here. I think I've been using Y to refer to... Yeah, I should just change this notation. I've been using Y in this proof to refer to an applicant, so I should definitely use a letter other than Y. I'm going to go for Z. Okay, so here, A and B are applicants. X and Z are employers. And then wonder if I can make enough room at the bottom of the page. This is going to be a close one. Okay. So we're now going to use property E. Z is an employer. It got matched to B in the end. It prefers A to B. So Z has previously proposed to A. Now we're going to turn around and use property A. I keep wanting to underline. Oh yeah. When I changed the letter Y to Z, I forgot to write Z here. Okay, so the question is, if A received a proposal from Z during the course of running the algorithm, how did it end up matched to X, who ranks lower than Z? Okay, because if you think whatever happened at the time Z proposed to A, either A was unmatched and got matched to Z, or A had a partner that was worse than Z, but then they would break off that engagement and get matched to Z, or A had a partner that was better than Z, but then by property A, forever after that, A's partner would also be better than Z, and hence also better than X. So we've reached a contradiction because we assumed that A ends up being matched to X, but we just proved that A cannot be matched to X at the end of the algorithm. That's what I meant to write. So that gives us that the matching is stable. Questions? Yeah?
Could you give us I'm a little confused as to the definition of perfect.
Oh, yeah, sorry. Perfect means that every person on both sides of the market belongs to one and only one match. Another way of saying it is that the matching defines a one-to-one correspondence between the two sides of the market.
What happened to the algorithm when the number of the applicants and the employers doesn't equal each other?
That's a great question. So the question was, what happens to the algorithm when the number of applicants and employers doesn't equal each other? And the answer is, if you were, I'll give you two answers. There's the one that's more efficient to reason about, and there's the one that's more efficient to implement and run. So you can guess what people do in practice. The answer that's easier to reason about is, let's say that the applicants outnumber the employers. You can artificially enlarge the problem instance by creating enough dummy employers that the applicant and employer sets are equinumerous. And then you just enlarge every applicant's preference list by putting all the dummy employers at the end of the list. We've now artificially created a larger instance of the problem that conforms to the specification because we have equal numbers of applicants and employers. These dummy employers have to have preference lists. You give them an arbitrary preference ordering over the applicants. Then you run the algorithm. You get some stable matching at the end. And anybody who was matched to a dummy employer, you just drop them from the matching. Those people end up unemployed at the end of the algorithm. But somebody would have to end up unemployed. If the applicants outnumber the employers, then you can't give a job to everybody. So that's a reduction from the imbalanced stable matching problem to the balanced one. A bunch of people are raising their hands. Just to finish my thought, the more efficient thing to do is there's a way to modify the code so that instead of creating these artificial dummy elements, it just doesn't treat the two sides as having equal size. And you need to have some extra case checking to deal with you run into some extra cases where somebody is unemployed because sorry, it's a little bit hard to describe. You need to do some minor tweaks to the code to incorporate the extra cases that arise from having an imbalanced market. But it can be done, and it runs more efficiently because if the employers are much less numerous than the applicants, then you don't want to pay the cost of enlarging the input to size n squared when the natural size is maybe 10n. Okay, question?
So is it different for like the applicant to choose an employer with like the employer choosing applicant?
That's a great question. So I was actually going to tell you about this. An interesting fact is that okay, define applicant A and employer X to be stable partners. If there exists stable perfect matching in which they are matched. Okay, and then when you run the proposal algorithm, every employer gets their favorite stable partner. And every applicant gets their least favorite stable partner. This is certainly not obvious. For the proof, I'll just say, see the book. Okay, but this means that there's a big asymmetry in the algorithm. The side that does the proposing gets a better outcome. And favorite stable partner might be very different from favorite applicant. You might not get your favorite applicant because there's simply no way to assign that applicant to you in any stable matching. Okay, but the side that does the proposing gets the best partner they could in any stable perfect matching. The side that receives the proposals does as badly as they possibly could. And so the answer to your question, what if you reverse the side and lets the applicants propose? In general, every applicant will be as good or better off, and every employer will be as good or worse off at the end of running the algorithm that way. Question, and this better be the last one before I turn you loose.
Yeah, about the preference list, is there like a rule to the preference list? Is there a rule to the preference list? You keep mentioning about that every applicant has a preference list.
Yes. The preference list is given as part of the input. So if you were running this algorithm, you would just need to supply an interface for people to enter their preference lists in some form. It could be just a list of names, or they could specify some ranking rule, and you could compute the list for them. Thanks, everybody. See you Wednesday.